In today's lecture, we are going to see a very important application of free electron theory of metals, particularly the Sommerfeld model. We will apply to discuss a very important phenomenon. You know, metals have free electrons according to the free electron theory of metals. And according to Rutherford model, these free electrons are fermions, so they obey Fermi Dirac Statistics, okay, and Pauli's exclusion principle. And in the discussion, we must take in under account the very important intrinsic property of electron, which is called a spin. Actually, taking all these things under account, we can discuss a very important phenomenon which is called thermionic emission. And in case of thermionic emission, we will discuss or derive a very important equation which is called Richardson equation or Richardson-Dushman equation. Okay. When you talk about electron emission, what does it mean? Actually, you know, in metals, the free electrons do not escape through the surface at 0 Kelvin temperature because the energy possessed by the electron at 0 Kelvin temperature varies from 0 to a maximum value which is called Fermi energy. And that Fermi energy is not sufficient for escaping the electron from the attraction potential barrier at the surface of the metal. Okay? And so these electrons do not escape through the metallic surface. But when we supply energy from outside source in any form, then it is possible that electron acquires such an amount of energy so that it can penetrate or it can escape through the surface of the metal. Okay? And this escaping of electron from the metallic surface is called electron emission. This has so many applications in physics, and this is the subject matter of both solid state physics and also of electronics, because you know the old electronic devices like diode, triode, tetrode, pentode, all these are based on the principle of thermionic emission. In fact, this electron emission is of 4 types. And the first one is very important, which is called photoelectric emission. You have definitely studied this photoelectric emission. In fact, when a metallic surface is irradiated by the electromagnetic radiation of proper wavelength, particularly shorter wavelength, then you know the electrons get emitted. And since here electrons are emitted due to the interaction with electromagnetic radiation or light, or you can say photon, so this emission is called photoelectric emission. Photo means photon. Okay. And similarly, when a metal is heated, then after a particular temperature, the electron gets emitted from the metallic surface, and that emission is called thermionic emission. Therm means temperature. Raising temperature, you can emit the electron from the metallic surface. Okay. But apart from these two very important processes of electron emission, there are other 2 processes. The another is called high field emission. In case of high field emission, what actually takes place? In fact, in this case, a high electric, or you can say strong electric field is applied on the metallic surface, and due to that electric field, the electron experiences electric force and they get pulled out from the metallic surface. Okay. So in case of high field emission, electric field is responsible for the electron emission. And fourth one is called secondary emission. Actually, in case of secondary emission, a metallic surface is heated by a stream of electron. This is also electron, and this striking electron strikes the electron inside the metal, provides it kinetic energy, and gaining that energy, this electron is capable to escape through the surface, okay, breaking the attraction potential barrier. Okay, so this is called secondary emission. But in this present lecture, our aim is to deal with the problem of thermionic emission only. And particularly in this thermionic emission, our aim is to discuss this Richardson equation. What is this Richardson equation, how it is derived, and how it can be experimentally verified? All these things we will discuss in this lecture. And this is our plan, this is our aim of this lecture. Okay. So now let us focus on thermionic emission. Actually, as I have told you, that when a metal is heated, then the electrons get energy in the form of thermal energy, and when the gained thermal energy is sufficient to break the attraction potential barrier at the surface of the metal, then the electrons get emitted or ejected from the metal surface. This ejection of electron by heating the metallic specimen, this is called thermionic emission. In fact, the ejected electron on heating are called thermions. Thermion means those electrons which are emitted due to heating of the metal. That is called thermions. Okay? And you know, electrons are charged particle, and so when the stream of electron will be ejected from the metallic surface, and by a suitable mechanism, you are able to flow these emitted electrons in a closed circuit. What will happen? You know, when these thermions will flow in a closed circuit, electric current will be constituted. Since this electric current is constituted by these thermions, that is the ejected electron after heating the metal, so such an electric current is known as thermionic electric current. This is called thermionic electric current. Okay. In fact, on what factors this thermionic current will depend, that was found by Richardson. Okay. Actually, Richardson has obtained the expression for the thermionic current density, particularly the saturation emission current density. When the maximum electron gets emitted from the metallic surface, that is called saturation emission. And what will be the current density due to that saturation emission current? That was obtained by Richardson. Okay, and the expression which defines the saturation current density, that is called Richardson equation or Richardson-Dussmann equation. In fact, you will see later on in this lecture that if J is the saturation emission current density, then this J is given by this formula. J equal to A times T square times e to the power minus phi over kT. Actually here A is a constant. When you say constant, actually you will see that this is a universal constant. The value of this constant will be same for all metals. Okay. T is the temperature of the metal in Kelvin unit, that is absolute temperature you can say. And this phi is a very important property of the metal. This is called work function of the metal. And this property varies from metal to metal. But for a particular metal, this work function will have a particular value. Okay. How this work function is defined, we will also see in this derivation. and K is a well-known universal constant which is called Boltzmann constant. So this is the equation which is called Richardson-Dushman equation, or in brief you can say RD equation, or simply Richardson equation. Now we will see how this Richardson equation can be derived using the Fermi Dirac statistics, or you can say Rutherford model, taking the spin of the electron under account. In fact, for this derivation you need the idea of Sommerfeld's theory of Sommerfeld's model for the metal. And actually I have provided some videos on it, but some more videos are required which have already been provided by me in the playlist of statistical mechanics. So I have actually added 3 videos on this subject in this playlist carrying from the statistical mechanics. So I will suggest you, if you have not watched those videos, that is how density of states will be calculated using the 3-dimensional model of metal, okay, 3-dimensional potential box of metal, what is Fermi energy and how it is calculated. All these things you have to learn, and in my playlist on this condensed matter physics I have added those 3 videos. So before going to these 3 videos you must watch them, okay, and then everything will be crystal clear to you, okay. So now let us see how this Richardson equation can be derived, and for this you can see I have shown in this figure a metallic specimen, and these horizontal lines actually represents the occupied state of the electron, and this uppermost line here is called Fermi level. You know, from definition of Fermi energy, you know, this is the highest energy, maximum energy of electron in a metal at 0 Kelvin temperature. So if you consider that your metallic specimen is at 0 Kelvin temperature, then energy of the electrons in that specimen will vary from 0 to EF. In other words, you can say that the maximum energy possessed by electron at 0 Kelvin temperature is equal to EF, which is called Fermi energy, okay. So the highest energy of electron in this specimen is EF, but you have learnt in Sommerfeld model that the potential inside the metal is uniform, is constant, and that potential I have shown in this figure is equal to W. And you can see the height of this potential W is greater than EF. W is greater than EF. Now see, if electron will be ejected, how much energy this electron should have? Can you say? You can see this is the surface, okay, and from here this electron emission will take place. So you can see, if W is the uniform potential inside the metallic surface, then at least this W energy is required by the electron for its escaping from the surface. It means if energy of the electron E is greater or equal to W, only then it can escape through the metallic surface. But you can see the highest energy of electron at 0 Kelvin temperature is what? This is EF, and this EF is less than W. So the electron cannot escape through the metallic surface at 0 Kelvin temperature, okay. So now let us consider this metallic specimen is heated, the electron gains thermal energy and its energy increases, and when its energy will be greater or equal to W, then the electron will escape through the surface. Okay, and you can see that from this figure I have considered that this much energy is equal to phi, and from this figure you can see that this phi plus EF EF is Fermi energy, this is equal to W. So phi is equal to what? This is W minus EF. So you can say if at least this phi amount of energy is given to the metal, then the electron will be just ejected. So phi is the minimum amount of energy required for ejection of electron. This phi which is W minus EF, and this is the minimum amount of energy needed for the ejection of electron. This is called the work function of the metal. Okay, so electron will be ejected when energy gained by the electron in the form of thermal energy will be either equal to phi or greater than phi. For example, let us consider that phi is equal to 3.5 electron volt. If you will supply an energy of amount 3.5 electron volt, electron will be just ejected. It will have no kinetic energy. But if you will supply an amount of energy which is greater than 3.5 electron volt, then electron will not only escape, but it will have kinetic energy too after escaping. Okay, so in this way the electron gets emitted or escape through the surface when the supplied amount of energy will be greater or equal to this work function of the metal. And as I have told you that this work function depends on the nature of the metal, it is different for different metal. So the different amount of energy is needed for ejection of electron in case of different metals. Okay. Now let us see. I have mentioned all these things here. You can see, you can note down these things in your notebook. EF is what? This is maximum energy possessed by an electron at absolute zero. It means 0 Kelvin temperature, and you know this is called Fermi energy. And W, this is the minimum energy of electron for its emission from the surface, and this is actually constant potential within the metal. Are you getting the things? Okay. And W minus EF, which is equal to phi, as I have told you, that this is the minimum energy used for the emission of electron, and this is called work function. And we also consider that the specimen of the metal under consideration has a volume V, although we will consider a specimen of unit volume for a calculation for simplicity. You will see later on. Okay. Now we also consider that this dN actually represents the number of electrons per unit volume in the momentum range P and P plus dP. It means in unit volume there are dN electrons, and these electrons have momentum between P and P plus dP. Okay, we consider. Then the value of dN will be what? That is found actually by the use of Fermi Dirac Statistics, and as I have told you, I have actually added those videos in this playlist which had been actually premiered earlier. So you can watch those videos on calculation of density of states and Fermi energy, where you will get the idea how this dN is calculated. Okay. Actually, when we apply the Fermi Dirac statistics, then we will see, and we will see in those videos that dN is given by this formula, G of P times F of E. What is this G of P? Actually, G of P is called density of states, and this density of state is what? This is actually the number of quantum states, or you can say eigenstates, in the momentum range between P and P plus dP. This is also written as G of P dP. In this way it is also written, okay, to indicate the range. So this is number of quantum states or the number of eigenstates of electron whose momentum lies between P and P plus dP. And you can see, if we ignore the spin of the electron, then this density of a state is found to be this much. You can see the calculation of this result, or you can see the proof of this result in my videos which I have added in this playlist. Okay, I am telling this thing several times, so that you must watch those videos. This is 4 pi p square dp over h cube. This represents the number of quantum states or eigenstates for the particles having momentum between p and p plus dp. But you know, electron has a property of a spin, and this spin state may be of two types, up spin and down spin. So if we will take the spin of the electron under account, then the number of eigenstates will be just twice of this. So this factor 2 is due to the two different spin states of the electron. Okay, so the number of quantum states of electron, considering its spin into under account, having momentum between p and p plus dp, that will be equal to 2 times of 4 pi p square dp over h cube. Okay, and you will learn it in those videos, or in the, if you have watched my videos on Fermi Dirac Statistics in the playlist of statistical mechanics, then you have certainly a knowledge of this. Okay, and what is this f of e? This is the well-known Fermi Dirac distribution function. Okay, and this Fermi Dirac distribution function, you will get a detailed discussion of this in my playlist of my channel named Statistical Mechanics. And you know, this f of e is given by this formula. This is 1 over 1 plus exponential to the power e minus ef over kt. See this. This is Fermi Dirac distribution function. So now you can find the value of dn. Dn will be equal to what? This is g of p times f of e, but g of p, you can see this is this much, 2 times 4 pi p square dp over h cube, and f of e, which is Fermi Dirac distribution function, this is this much. Okay, now actually our aim is to express this 4 pi p square dp, which is actually an elementary volume in momentum space, in terms of the velocity components of the electron, and how we can transform it in terms of components of velocity. Let us see. You know, if we consider that v is the velocity vector of our electron, and vx, vy, vz are its components in x, y, z direction, then v is simply equal to vxi plus vyj plus vzk. And so the square of its modulus will be equal to this much. This is vx square plus vy square plus vz square. But you know that p, which is linear momentum, that is equal to mv. So when you will multiply by m square in this equation, then you will see that this equation will change into terms of momentum. So p square will be equal to px square plus py square plus pz square. Here px means mvx, okay, and py means mvy. In this way you can transform it. Okay, actually this p square equal to px square plus py square plus pz square, you know, this is actually this represents actually a sphere of radius p. Okay, because you know the equation of an sphere is x square plus y square plus z square equal to r square. Okay, so in momentum space there will be a sphere whose radius will be equal to p. So the equation of that very sphere will be p square equal to px square plus py square plus pz square. So I have mentioned it here that it represents a sphere of radius p. Okay. Now, if we consider that there are two concentric spheres, see here, O is the common center. The inner sphere has radius p and the outer sphere has radius p plus dp. Then can you say what will be the volume enclosed between these two spheres? This is actually simply the differential of change of the volume of the sphere of radius p, and volume of the sphere of radius p in momentum space is 4 by 3 pi p cube, and its differential will be 4 pi p square dp. Okay, so this is the volume of the region between these two spheres. But when you say momentum is between p and p plus dp, then in terms of components you can say that the x component of momentum lies between px and px plus dpx, y component lies between py and py plus dpy, z component lies between pz and pz plus dpz. So in terms of components you can say that the volume in momentum space between px and px plus dpx, py and py plus dpy, pz and pz plus dpz will be what? That will be equal to dpx into dpy into dpz. Just as in Cartesian coordinate, you know the volume element is dx into dy into dz. This is the volume element in position space. And here we are talking about the volume element in momentum space. So at the place of position coordinate, there are momentum coordinate. Okay, but that will be equal to this volume, the volume of this shaded region, and the volume of shaded region you have seen, this is 4 pi p square dp. So this 4 pi p square dp, which occurs in this equation 1, that is simply equal to dpx times dpy times dpz. That's why we can replace this 4 pi p square dp by this factor in that equation 1. So you can write the expression for dn now in this way. This is 2 over h cube, you can see 2 over h cube, and at the place of 4 pi p square dp, I have written here, you can see dpx times dpy times dpz, and divided by 1 plus e to the power e minus ef over kt. Okay, but as you know, px is the x component of momentum of electron, and so this px can be replaced by m into vx, py is m into vy, and pz is m into vz. So these px, py, pz has been replaced by m vx, m vy, and m vz. But you know m is mass of electron, which is constant, so all these m will be outside of the differential operator, and so that will be m cube, and this equation will now become dn equal to 2m cube over h cube times dvx, dvy, dvz, okay, and over this much. This is 1 plus e to the power e minus ef divided by kt. Okay, but actually it is found that at room temperature, this E minus EF is much greater than this KT. Much greater than this KT. Actually, this KT at room temperature is almost of the order of 0.03 electron volt. And this E minus EF is almost 20 times of KT. 20 times of KT. So you can say that this E minus EF is much greater than KT. And if this E minus EF is much greater than KT, then can you say what will be E to the power E minus EF over KT? That will be much greater than 1, because you know e to the power x is equal to 1 plus x square over 2 factorial plus x cube over 3 factorial. If x is much greater than 1, then you can see due to the presence of these higher powers of x, this e to the power x will be much greater than 1. Okay, so this exponential factor in the denominator of equation 2 is much greater than this number 1. Okay, and since exponential factor is much greater than 1, so in denominator we can neglect this 1. So after neglecting this 1 in denominator, our result will be this: dn will be equal to 2m cube over h cube times dbx dby dbz over e to the power e minus ef over kt. Okay, now take this exponential factor in numerator, so the power will become minus and result is 2m cube over h cube times e to the power minus e minus ef over kt dvx dvy dvz. Okay, now break this exponential factor in two parts. You can see this will be 2m cube by h cube times e to the power ef by kt. Minus minus will become plus, and e to the power minus e by kt. But what is this e? You know, our electron is free. We are talking about free electron. It means its potential energy is 0. And if potential energy is 0, its total energy E is in the form of its kinetic energy, which is half mv square. So at the place of E, I have written here half mv square. Okay, so this exponential factor will be e to the power minus half mv square by kt, and this dvx dvy dbz at each. Okay, but you know, v square is equal to vx square plus vy square plus vz square. So in terms of components, you can write this v square in this way. So dn now becomes 2m cube over h cube times e to the power ef by kt times e to the power minus m times vx square plus vy square plus vz square and divided by 2kt. Okay, and this factor is at h. Okay, now let us write this equation in this manner, in a symmetrical manner. This is 2m cube over h cube e to the power ef by kt times e to the power minus m vx square over 2kt dvx e to the power minus m vy square over 2kt dvy and e to the power minus m vz square over 2kt dvz. Okay, now let us consider our metallic specimen. The surface of our metallic specimen lies in yz plane. This shaded region actually represents the surface of the specimen. This is surface, and this surface lies in yz plane, and x-axis is perpendicular to this yz plane. Okay, so when this will be heated, then electron will be ejected in x direction. Now our aim is to find what will be the number of electron per unit volume ejecting in x direction, whose velocity in x direction lies between Vx and Vx plus dVx. Okay, irrespective of its velocity in y and z direction. It means in y and z direction, velocity will have all the possible values. But in x direction, we are talking about only those electrons whose velocity lies between Vx and Vx plus dVx. So how we can obtain it? For obtaining this, we must integrate this equation which I have written here for dn. For dnx, you can see I have considered that this dnx is the number of electrons per unit volume with velocity between Vx and Vx plus dVx, okay, irrespective of the velocity in y and z direction, okay. Then this dnx can be obtained by integrating the exponential factor for Vy and Vz for all possible values of Vy and Vz, and taking the x component at each. So dnx now will be equal to 2m cube over h cube times e to the power ef by kt e to the power minus m vx square over 2 kt dvx. But this e to the power minus mvy square over 2 kt dvy will be integrated between minus infinity to plus infinity, because in classical physics the velocity may have a value between minus infinity to plus infinity. This is actually classical idea. Don't think about the special relativity, okay. And similarly Vz will also have value from minus infinity to plus infinity. Now how this integral will be evaluated? You can definitely have an idea of the Gaussian integral of this form. You have definitely studied in your course on mathematical physics in gamma function that integral e to the power minus ax square dx from minus infinity to plus infinity. This is pi over a square root of pi over a. So you can compare these two integrals from this formula. Here you can see at the place of a in our integral, at the place of a there is what? At the place of a there is m divided by 2 kt, m by 2 kt. So the value of this integral will be pi over m by 2 kt square root, and that will be 2 pi kt over m's square root. And the second integral is also same. You know, in case of definite integral the form of function is meaningful, not the function. Here at the place of Vy there is Vz, but limits are same, form is same, so value will be same, okay. So both of these integrals will be a square root of 2 pi kt over m, and when they will be multiplied there will be a square, okay. So dnx will be equal to 2m cube over h cube times e to the power ef by kt times e to the power minus mvx square over 2 kt dvx times a square root of 2 pi kt m over m, okay. So when you will square this, square root will cancel, and dnx will be what? Dnx is equal to 2m cube over h cube times e to the power ef by kt times e to the power minus mvx square over 2 kt dvx times 2 pi kt over m, okay. Now you can see this m will cancel out, and here there will be a square, okay. And so our result is dnx equal to 4 pi m square kt over h cube times e to the power ef by kt times e to the power minus mvx square over 2 kt dvx, okay. Now these we are talking about only those electrons which are emitting in x direction. You know, when there is a flow of charge in a particular direction, only then current is constituted. So we are talking about the emission of electron in x direction, okay. And we have calculated the number of electron per unit volume which is ejecting in x direction, but its velocity lies between Vx and Vx plus dVx, okay. But you know, you have seen earlier that only those electrons are emitted, as I have told you, only those electrons can escape through the surface of the metal whose energy is greater or equal to W. Only then electron can escape. Okay. Here energy means kinetic energy of the electron, and we are talking only those electrons which are ejecting in x direction. So we will talk, when we will talk about kinetic energy, then this will be half mvx square. So only those electrons will be emitted whose energy E, which is equal to half mvx square, will be greater or equal to W. Okay? Are you getting the things or not? I have already explained this. And so in terms of Vx, you can see that only those electrons will be ejected in x direction whose velocity Vx is greater or equal to a square root of 2W by m. Only those electrons will be ejected. Okay. So now our aim is to find how many electrons will be ejected in unit time, which will move through unit area, because our aim is to find the current density, and you know current density is the current passing through unit area. Okay, and if we will know the number of charge carrier, we can find the current and current density. So now let us consider that this capital N represents the number of electrons arriving per unit area per unit time in the YZ plane. Okay, then what will be this? This number can be obtained by integrating this equation 3 for the limits of Vx between what? Minimum value of Vx for ejected electron will be equal to root over 2W by m, and its maximum value will be infinity. So when this equation 3 will be integrated with respect to Vx between these two limits, you will get the total number of electrons passing through unit area per unit time. Okay, so you can see how you can find it. Since we are talking about the number of electron passing through unit area in unit time. So now let us consider that we consider a cylinder here, and its cross-sectional area, let us say S is equal to 1. 1 means 1 meter square or 1 centimeter square. And consider if an electron is here at 0 time and here it is at 1 second, then how much distance it will cover? Since Vx is its velocity, so in 1 second it will cover a distance of Vx. So those electrons will describe a cylinder whose cross-sectional area is equal to 1 and length is equal to Vx. So what is the volume of this cylinder? Since volume is equal to area of cross-section times length, so this will be 1 into Vx. So Vx is the volume, and dnx is the number of electron per unit volume in x direction. Okay, whose number of electron per unit volume whose velocity in x direction lies between Vx and Vx plus dVx. So when you will multiply Vx by dnx, then you will get the number of electron passing per second through unit area in x direction. Okay, in x direction. But only those electrons whose velocity lies between Vx and Vx plus dVx. And if your aim is to find the total number of electrons, then you must integrate it for the entire range of velocity. So n will be equal to integral of Vx into dnx. Have you understand this point or not? Vx here represents the volume because this is Vx times 1. Okay, and velocity of the ejecting electron is at least a square root of 2W by m, you know, and its maximum value will be infinity. So the limits of integration will be root over 2w by m and infinity. Okay, and here dnx, you know this expression is the value of dnx and vx is here. Okay, now except the factor containing vx, all things are constant. So take those constant outside of the integral. This is 4 pi m square kt over h cube times e to the power ef by kt. And inside the integral, there is e to the power minus mbx square over 2 kt vx dvx. Now you can see how this integral will be evaluated. Actually, this integral can be evaluated by a method of substitution. For evaluating this integral, let us suppose that vx square is equal to t. Okay, and now take the differential. When you will take differential of vx square, this will be 2 vx dvx, and differential of t will be dt. Okay, so vx dvx will be equal to dt over 2. Now see, our aim is to evaluate this integral. See this, and now this integral can be written as in this way, replacing vx square by t. So this will be integral e to the power minus mt over 2 kt, and vx dvx, you can see this is dt by 2. Okay, dt by 2. And now you can see this is simply in the form of integral of e to the power minus ax dx. And what is this? This is e to the power minus ax by minus a. At the place of a, there is m divided by 2 kt, m by 2 kt. So its integral will be equal to what? E to the power minus mt by 2 kt and divided by minus m by 2 kt. So that will be minus 2 kt by m, and this factor 2 in denominator is here. Now this 2 and this 2 will cancel out, and this is minus kt over m. Okay, and now replace again this t by vx square. Okay, so at the place of t, now I have written vx square. So this is the integral. Now let us substitute the limit. Limits are a square root of 2w by m and infinity. So when you will put the limit, what will be your result? This will be minus kt over m e to the power minus mvx square over 2 kt, and these are limits. Now put the limit. You can see since here there is minus, so minus will become plus when the limits will be interchanged. So I have written here plus kt by m, but first of all I have substituted this lower limit because minus has been made plus. So this is e to the power minus m by 2 kt, and at the place of vx you have to write this lower limit. Okay, and since there is a square, so this will be 2w by m. And now put this in upper limit. This is e to the power minus infinity. Now this m and m will cancel out. This 2 and 2 will also cancel out. And your result is kt over m times e to the power minus w by kt. And you know e to the power minus infinity is what? This is 0. So I have written here 0. So finally we get that this integral is kt over m times e to the power minus w by kt. Now let us substitute the value of this integral in this equation number 4, and then you will get this n, which is number of electrons ejecting in x direction per second through unit area. Mark it. So this number n is now given as 4 pi m square kt over h cube e to the power ef by kt times kt over m times e to the power minus w over kt. Okay. Now see, this m will also cancel out, and now combine these two exponential factors. Okay, after combining, our result is n equal to this much. This is 4 pi m k square t square over h cube, and e to the power, if we will take this minus as a common factor, then this will be w minus ef by kt. Okay, but you have seen that this w minus ef is equal to what? We have denoted it by phi, which is called work function of the metal. Okay, and except this t square, this 4 pi m k square over h cube, you know this is a universal constant, and I have written that universal constant by the symbol a naught. So a naught has been written at the place of 4 pi m k square over h cube. So this n is equal to what? This is a naught t square times e to the power minus pi over kt. So you can see that actually the number of this ejected electron, which is the number of electron ejected in x direction per second through unit area, okay, through unit area, mark it, that strongly depends on this temperature. Okay, with increase in temperature T, this n will increase. Okay, and as that metal is heated and heated and heated, temperature is raised and raised, and number of ejected electrons also increases. But it is not possible that always this number will increase. After some time, the number of ejected electrons per second through unit area will become constant. That is called actually the saturation state. Okay, that is called saturation state. So at a particular temperature, electron emission becomes maximum, and this is called saturated electron emission. In fact, in that condition, what will be the current density? That is saturation emission current density. You know, current density is what? This is current passing through unit area. Here, n electron passes in 1 second through unit area. So when you will multiply this n by the electronic charge of a charge carrier, then you will get the total charge passing through unit area in unit time. Total charge passing through passing in unit time is current, and when you say unit area, that will current density. So this J is equal to E times N. Okay, E times N, and N you have already obtained here. So this will be E times A naught times T square e to the power minus pi over kt. But you have seen that A naught is a universal constant, and E is electronic charge, which is also a universal constant. So the product of this E and A naught will be another universal constant. So finally we get J equal to AT square times e to the power minus pi by kt. And can you say what is this equation is what? I have mentioned this equation in the beginning of my lecture. This is nothing, this is simply the RD equation. This is Richardson equation. Okay. So in this way we can derive this Richardson equation, and I think definitely you have clearly understand how this equation can be derived. Okay. So if you will watch the video seriously, write down these things in your notebook, everything will be clear. Okay. And this J is strongly temperature dependent, you can see. Now we will see the experimental verification of this Richardson equation. Okay, let us see. Actually we can see the experimental verification in this way. You can see this equation A. From this equation, if you want to find the value of J over T square, see here, then J over T square will be equal to this much. Okay. Now take the natural log both sides. So this will be log J over T square equal to log A minus phi over kt. because this will be log e to the power minus phi by kt, that will be minus phi by kt times log e, but log e is 1. Okay. So log j over t square is equal to log a minus phi over k times 1 over t. See this equation. This is simply y equal to c plus mx. This is equation of a straight line with negative slope. The slope of this straight line is minus phi by k. So the graphical plot of this log j over t square in against of 1 over t is a straight line. Since when we draw this graph, then it is found that the graphical plot of log j over t square in against of 1 by t is a straight line. So this verifies the RD equation. This is this indicates its validity. Okay. And actually, by the use of this graph, we can also obtain the constants like work function. You can see if this angle is psi, then tan psi is the slope of this straight line. But comparing with the standard equation of a straight line, you can say that this slope is equal to minus phi over k. So phi will be minus k times tan psi. So measuring the slope of this straight line, we can measure the work function of the metal. And when this value of work function is compared with the standard value of work function of the metal, which have been measured by other methods, then you will see that the two values resemble. They are identical. This is also the proof of the validity of this RD equation. Okay. So in this way you can experimentally verify this RD equation. I think definitely this session was very helpful and very joyful for you, and as I have suggested, you must watch the videos on calculation of density of states and Fermi energy, which I have added in this playlist. Okay, so go through the playlist of condensed matter physics and watch the 3 videos. Okay, thank you very much.